We go on from where we left off yesterday. Two of the more important choices that you have to make when you are implementing systems thinking, we said were setting the boundary and also setting the scale for your inquiry. And we discussed what we mean by boundary setting and pointed out that it is not a very straightforward, this is not a very straightforward matter, and you have to be careful about the boundaries of the narrow system of interest. And keep always in mind that these boundaries need to be moved, need to be expanded or contracted. Contracting the boundary makes it easier for you to model the system. Expanding it makes it harder to handle. But of course expanding it will increase perhaps the... Arkadaşlar girmeyin sınıfa. Bundan sonra girmeyin. Geç geldiyseniz girmeyin. Anladınız mı? Kaç kere hatırlatacağım? So setting the boundary, therefore, needs careful thinking. The best we can do in setting the boundary is to remember that such boundaries must maybe widen later on or contracted as necessary. Now, failure to do this, failure to think that the boundary once set is permanent, can cause what we sometimes call, or Churchman calls, environmental fallacy. A fallacy is an error, okay? Environmental fallacy is a fallacy because we fail to recognize the environment from the system. An error committed by setting the boundary too tight, usually, is what we call environmental fallacy, and it's the most common and serious mistake committed in the practice of industrial engineering. So we should really be concerned about this, this possibility. An environmental fallacy will be committed if we focus our attention on one part of the system only and forget about the rest of the system. This is clear, but it takes time to realize its importance and what to do about it. Another point is that a fallacy, such a fallacy will be committed when you confuse efficiency and effectiveness. Confusing these two is committing an environmental fallacy. Now, let's take some examples. In a hospital, just consider a hospital, and we try to improve the conditions in the hospital and decide to maximize the efficiency of each department of a hospital. You know that hospitals are composed of many different departments. There's a department for acute diseases. There's a department for children's section, etc., etc. There are laboratories. There are facilities for X-raying, etc. And if you take each department on its own and try to maximize the efficiency of the department, it does not necessarily follow that the hospital will work effectively. Okay, you have to consider the entire hospital if you want your hospital to work effectively. Effectively means if the hospital is going to serve its long-term objectives, and that's what you want, actually. Another example could be trying to minimize inventory costs. This is something, as industrial engineers, you need to do all the time. To minimize costs, and especially inventory costs are significant. A focus on minimizing inventory costs will lead to a fallacy, since inventories cannot be decided independently of production, of marketing, of procurement, of distribution, of maintenance. You see, you have to consider the entire operations altogether. If you just focus on minimizing inventory costs, maybe you will be losing sales. Your profitability will suffer. If you try to minimize inventory costs all the time, for example, you need to know what data do you need to know if you try to minimize inventory costs. What sort of data do you need? No, inventory costs. There's something called the inventory holding cost, right? You're familiar with this. What is the inventory holding cost? Where are you going to learn it? I mean, where are you going to get that data? Who will tell you what the holding cost is? It's not very clear. You might ask the accountants, for example, or you might ask the finance department. If you ask the finance department, what is the cost of holding 1 lira's worth of inventory in stock for 1 week, let's say, you need a number. Huh? The finance officer has to give you a number. What number is he going to give you? How is he going to calculate that number? What is it? It's an opportunity cost. What is it? It's the cost of spending 1 lira on inventories instead of something else. How is this figure, how can this figure be calculated? You have to know the return of all the other things that you can do with that 1 lira and compare it with the cost of putting it into inventory. It means that you have to optimize all your operations. You have to know what operations will optimize, will maximize, for example, the long-term profitability of the organization. Can anybody do that? It's very difficult, isn't it? I mean, but if you just assume that you can minimize inventory costs by taking a number from the finance department, then this implies that the finance department has determined and optimized all the other operations of the firm and has been able to compute the correct opportunity cost of 1 lira. Probably this will not be true, okay? But I'm not saying that you don't have to compute or you don't have to minimize inventory costs. But when you are minimizing inventory costs, you should always keep in mind that the numbers that you use for example, unit holding costs are subject to further questioning. It takes place in the other department. Similarly, for example, marketing. Marketing and production departments are usually have this conflict in many organizations. The marketing department would like all the finished goods in inventory, waiting and ready, because there might be an opportunity of a sale. And the production department does not like, and if there are multiple products, of course, there has to be multiple production runs for producing different types of products, which is a headache for the production department. And marketing and production are usually in conflict in these matters. And the production, for example, would like to minimize work in process inventories. They would like to keep the level of inventories as little as possible. And marketing has other ideas about this. For example, if you do that, you may be losing some business opportunities, some sales may be lost, etc. Okay? So you cannot just focus on minimizing inventories. If you do that, it will be probably an error, an environmental error or fallacy. Now, you have already read Akoff. He defines environmental fallacy as there's a distinction between doing the right thing and doing things right. This distinction, he says, is fundamental. The righter we do the wrong thing, the wronger we become. The righter you do the wrong thing, the wronger you become. You don't become righter, you become wronger, although you are trying to do the wrong thing righter. Okay, it's a very nice expression. If you made an error doing the wrong thing and correct it, we become wronger. It is much better to do the right thing wrong than the wrong thing right. Why is it much better to do the right thing wrong? Yes, but a better way of saying is to learn, to learn. If you do the right thing wrong, well, doing it wrong, of course, is not very good, but it's not too bad, you see. It provides an opportunity for you to use feedback from your wrong conclusion and correct that mistake and therefore learn about the system. So doing the right thing wrong is better than doing the wrong thing right. That's what we mean by environmental fallacy. Environmental fallacy is doing the wrong thing right. For example, like minimizing inventory costs. If you minimize the inventory costs, doing it right, doing the minimization right, maybe it will be bad for the entire company because it's the wrong thing to do. You have to look at the entire operation, and you have to, for example, maximize long-term profitability instead of minimizing short-term inventory levels. The other critical decision we have to make in systems thinking is separation of scale. This is very, very significant also. And in order to explain this, last year I decided to review the concept of a state. Normally, the concept of a state is fundamental in engineering. And all engineers understand this intuitively. But it's not so with our department. Our students have difficulty in understanding this. Although we send you to take courses in electrical engineering where they teach all those things, it's better to repeat it a little bit. Okay, so let's see what we mean by a state. This is a fundamental concept that cannot be defined any more than the concept of a set can be defined. Can you define the concept of a set? It's difficult, isn't it? You can say it's a collection of objects, but no more than that. State is similar. In order to define it, let us use some formalism. Let us consider a physical system that transforms a single input into a single output. And let us assume that these inputs and outputs are functions of time. So Vt is a function, it is the input function, and Yt is the output function, let's assume. Now, if you know the structures and the processes that make up the system, just consider the system as if it's a black box. An input is coming in, and an output is going out. The black box contains several things. The things that a system contains usually can be described in three ways. There are structures, there are processes, we have gone over these, and what's the third item? There are relations between these, okay? Three. So let's assume that we know all of those. If we know the structures and processes that make up the system and also, of course, the relations between them, then complete knowledge of Vt, that is input, over the interval from -infinity to the present time. If we know the input over the entire history from -infinity is just a way of indicating we include the entire history, up to the present time t, then this knowledge is sufficient to determine Yt over the same interval. We can compute Yt over the same interval if we know all the structures, everything about the system, and the input in its entire history, during its entire history. But if the input is known only over a restricted interval from, let's say, t0 to t instead of from the beginning, then we need information at some time t1 between t0 and t in order to determine the output over the same interval. This is a very fundamental statement. This is all about control and systems, engineering systems. Do you understand this? Okay? If you do not know the entire history of the input signal, then, but only we have the input signal for a limited interval of time. In order to compute the output signal for the same limited interval of time, we need something else. What do we need something else? We need something else which occurs at a time t1 within that interval. This information, this what we need to know at time t1 is known as the state of the system at t1. We need to know the state of the system at t1. What does it consist of, this knowledge, or this state information? It consists of the levels, or the values, levels, of all the structural and process variables. Or actually, we call it the state variables at time t1. Okay? The system itself is composed of structures and processes, and there are associated variables. As I have told you, for example, x could be a variable for a structure like capital investment. And dx to dt, its time derivative, could be a variable which is the annual investment or annual depreciation, etc. All those processes, one is a structural variable, the accumulated capital, and investment is a process variable. So if we know the levels, the values of all those variables at time t1, this information is known as the state of the system at t1. If we know this, then we can compute the output signal for the restricted interval. Now, so this is the concept of state, and associated with this, the concept of state variables. Now, you are familiar with state variables, actually, in operations research courses, from your courses. Like, for example, in dynamic programming. In dynamic programming, where you compute recursively, a recursive process is used in dynamic programming, which discovers an optimal trajectory or an optimal output. And then there you have state variables, decision variables. You should remember the state variables in dynamic programming are exactly what we mean by state variables in general here. Another example could be from queuing theory. You have taken some queuing classes. In queuing theory, there are the simplest type of queues that we teach in this department are what we call birth and death queues. Birth and death queues. These are Markovian queues, for which the limiting distributions can be easily computed by writing balance equations. Probably you have seen these. Now, just consider such a queue. The simplest queue is the MM1 queue. You remember the MM1 queue? The input is Markovian. The service duration is also exponential. That is Markovian. The time between arrivals is distributed exponentially. The time of the service duration is distributed exponentially. There is one server, and an infinitely long queue can accumulate in front of this server. This is called the MM1 queue. Now, in the MM1 queue, for the MM1 queue, we do not ask you to compute the time-dependent solution of the MM1 queue, but we compute the limiting solution when time goes to infinity. But just assume that we are interested in a time-dependent solution. For example, the queue is a barber shop. There's a single barber serving the customers. There's one seat. And there's an infinite capacity for waiting. People can wait outside the barber shop. The barber shop opens in the morning at 8 o'clock when there are no customers, and gradually some customers start to come in. If I ask you, for example, the state of the system at 10 o'clock, how could you tell me the state of the system? What information do you need to give me? What is the number that determines the state of the system at 10 o'clock of this barber shop? No, arrival time and service times are stochastic. They change according. Yes, the number of the customers in the queue. If you give me the number of the customers in the queue at 10 o'clock, I know everything about the system. What does it mean to know everything about the system? Suppose the number is 6. I tell you that there are 6 customers at 10 o'clock in the barber shop. Then you will know that one of these 6 customers must be sitting in the chair and having his hair cut, and the other 5 are waiting. Is this complete information about the system?
No.
What else do you need to know?
When it is checked.
Yes, you may need to know how long has he been taking this service. Huh? Is it 5 minutes that he has been sitting in the chair, or 10 minutes, or what? But you see, we don't need this information. Why don't we need this information? Because of the memoryless, or the Markovian property of the exponential distribution, the service time, the remaining time to the completion of the service, we call it time to service, let us say, it's a random variable. It is independent of how long the service has already taken place. If that is the case, then the number 6 is sufficient. I don't need any further information. So the number of customers in an MM1, or in fact most Bertrand queues, is the number of customers. But of course, the assumption here is that the service duration is distributed exponentially. Do you think the service duration is distributed exponentially in a barber shop? Probably not. I mean, if this man has been sitting in the chair for 20 minutes, then you cannot say that the remaining time can be anything. Probably it will not take more than 5 more minutes, because a haircut doesn't take longer than half an hour at the most. So in the barbershop example, the assumption of exponential service time distributions is not realistic. If the distribution is not realistic, then the state of the system would be a vector. Not only the number of customers would be needed, but also what you have said, or the elapsed service time would also have to be given if the distribution is not exponential. Okay, is this clear, the concept of a state? It gives you complete information about what is happening in the system. All the variable values, the values of all the variables are known at time t. That's, and these variables are called state variables. Usually, in very, very simple systems like the MM1 queue, it can consist of a scalar, one number. But in realistic system, it's a vector. It's a state vector containing many, many variables. So that's the idea of a system state. In this sense, the state of the system is related to the memory of the system, you can say. For another example of system state, consider linear differential equations. Again, you have taken the differential equations course, and you have probably solved some simple linear differential equations, which are very easy to solve. When you solve such equations, the solution comes in 2 parts usually. One part is time dependent. There's an exponential function usually with an exponent t, minus t, which decays in time. And there's a part which is constant, which is not dependent on. Do you remember these exercises? Of course you don't. Well, you must have seen these in differential equations courses. Now, when we let time go to infinity, the time-dependent part goes to 0, and you get the steady-state solution, or the limiting solution. Well, anyway, suppose that you solve such an equation, linear differential equation with constant coefficients. If the coefficients are constant, they are very easy to solve such equations. Once the form of the complete solution is obtained in terms of arbitrary constants, you see, when you are solving a differential equation, you integrate. You have to integrate differentials. When you integrate, then you need constants of integration. These constants are not known generally. You have to find them from somewhere. You have to obtain the information about the constants from somewhere. Where do you get those? You get them from initial conditions. These constants can be determined by the fact that the system must satisfy, in differential equations courses, probably the term used was initial conditions. But actually, these are boundary conditions, because the differential equation doesn't have to be in terms of time only, not t. It could be space also, distance. You can solve a differential equation as a function of distance. So boundary conditions is a better word. So the boundary conditions at time t0. When these are known, then you can calculate those unknown constants from these conditions, you remember. These boundary conditions can be termed the state of the system at time t0. Usually, the differential equation concerns some physical system, and the situation of the physical system at time t0 is given to you. From that information, you can compute the, well, you have computed these things without knowing what you were doing probably. This is it, okay. Intuitively, the state of a system separates its future from the past. So the state contains all the relevant information concerning the past. The state of a system is represented by a vector showing the values of all the state variables at time t, and we call this the state vector. Now, let us see the set of all these states. This is called the state space. Another very fundamental engineering concept is the concept of a state space. And let us see how large such a space can be by using an example. Let us assume that we have a 7 by 100 array of electric bulbs, light bulbs. Sometimes not any longer, but in the past, such panels were put on squares in cities where information is by lighting some of the bulbs, you can form letters, and these letters move. And you get information about the temperature or whatever information is provided. Still, these are available, but now instead of bulbs, they use other types of display panels. Let us consider such a 700 bulbs, 7 high, 100 long, okay? That can allow 20 letters to be written by lighting some of the bulbs. 100 divided by 20 is 5. So 5 letter bulbs in a row, 5 by 7. 5 by 7 is 35. 35 bulbs are used to write one letter. Okay? So 20 letters can be written. Now, this system will have 2 to the power 700, which is 10 to the power 210 different states, depending on which bulb is on and which bulb is off. Okay? Since each bulb has 2 states and there are 700 such bulbs, the state space is this much. You see, the number of atoms in the universe is estimated as 10 to the power 73, and compare it to the state space of our simple display panel, this is a negligible small number, 10 to the power 73. You can assume it to be 0 when you compare it to that number over there. Okay? So the state space can be huge, inconceivably huge. We cannot conceive how huge this number is. Okay? Some students ask me, how do you know that the number of atoms in the universe is 10 to the power 7? I don't know. Somebody told me. Okay. Probably this is a realistic estimate. Now, if this is the state space, we are in big trouble. I mean, if we need to compute, for example, the optimal state of a system out of such a huge number of states, we are in deep trouble. But fortunately, not all the states of a system need be relevant for decision making. In many cases, knowledge of aggregates or averages is sufficient. This is what we mean setting the scale or separation of scales. For example, you are studying traffic problems. Let us assume that we have determined a region, a part of Ankara. There are streets, main streets, side streets, etc. And we are studying the traffic in this region. What would be the state space of our inquiry? It would be, at all times, the number of all vehicles, bicycles, motorcycles, cars, buses, etc., and also pedestrians, people, at each location in this system. That would be the state space. This is something maybe much greater than the light bulb example. The light bulb example was a very simple system of 700 bulbs. This is inconceivably huge. But we don't need to know the exact position and speed of all vehicles. Let us assume that we are not interested in pedestrians, just the vehicles that are on the road network at all times. Often a knowledge of time averages is good enough. Traffic systems are studied a lot in operations research. Industrial engineering, transportation systems is a very important area for industrial engineering work, and maybe some of you will work on these. Congestion systems, traffic regulations, etc. And you need to know only the average number of cars passing in every 10 minutes at this cross-section of the road, for example, might be good enough for you. A better example can be given from engineering. Suppose that a civil engineer is designing and constructing a bridge. Now, this bridge is going to be made of materials like concrete and steel, right? And a state vector of all the molecules that make up the bridge, because materials have molecules in constant movement. Maybe the state of the bridge needs to be aware of all the positions and the speeds of all the particles in the materials, but because this will affect the strength of the materials, etc., and the way the calculations of the bridge have to be carried out. But it doesn't happen like that. The engineer doesn't need to know particle physics. He can use only, for example, averages like the strength of the steel, tensile strength or ductile strength or the density, etc. These averages are sufficient for the civil engineer to design a safe and a reliable bridge. Okay? This reduction in the number of the relevant system states is achieved by separation of scales. That is by deciding what level of detail is relevant for decision making. So 2 decisions: what boundary and what scale. These are the essential. For example, here is a figure from an article we omitted this year, but last year it was a reading. As you can see, from particle to atom, molecule, cell nucleus, brain, cell, brain, nervous system, individual, which is yourself, local community, state, nation, world civilization, world ecosystem, planet Earth, solar system, galaxy, universe. So there is such a hierarchy of states. As we go up, if we, for example, study only the solar system, then we say that we are at a high level or a large scale. It's like a map, a very large scale map, 1 to 1 million, for example. On an A4 size paper, you can map all the land area of Turkey, for example. That's a large scale or coarse scale. And at the bottom, we have fine scale or small or low scale. All these underlined terms are used interchangeably. That's why I'm showing this to you. Don't be confused. Small means fine and low. Large means coarse and high. In an extreme case, the extreme case, when we look at the very highest level at a system, then the system what is represented with what we call a black box. Sometimes, in extreme cases, the scale can be so large that the system is defined as a black box. When not all the details of the transformation process is needed, you don't need to know what all the details of the transformation process is taking some inputs and producing some outputs. For example, in the sawmill example, logs are coming in and sales revenue is coming out, if you can define the transformation as such. And a black box representation might be sufficient for the purposes of your inquiry in some situations, which shows only the input and only the output. That's what we mean by a black box representation, highest level of scale. Finally, I have not really, I have forgotten to put some examples, but the final concept we discuss on a single slide here, but I'll give you examples in words, is the concept of emergence. This concept, emergence, is the most fundamental attribute of a system. Now, you are familiar with this because you read Eckhoff's articles. You know what it means. Emergence is a property that does not belong to the parts of the system, but which comes about when all the parts of the system interact and work together. It's a synergetic output. The synergy, you know the concept of synergy, which means that the whole is greater than the sum of its parts. Emergence means that the whole is greater than the sum of its parts. An acceptable definition of the concept of system, and I like this definition best. I mean, if you ask me to define a system very shortly, I would give you this definition. A system is a set of interrelated components with emergent properties. This tells us all the essential aspects of a system. Emergent properties. An emergent property normally appears at higher levels of scale as a result of interactions at lower levels. Examples are given in the Eckhoff case. The motor car example, you remember, it consists of many parts. There's the motor, there are the wheels, there's the steering mechanism, there's the body, etc. All these parts come together. We are looking at the automobile at a lower scale now, considering the carburetor, everything, the fuel injection system, the brakes, etc., all of them. They come together, and when they work together, the car moves. None of the parts on its own is able to move and provides transportation. So if now the emergent property of being able to provide transportation occurs at this higher level, okay? Due to the interaction of the parts at a lower level. Another emergence example I used to give, I don't have a, okay, I have a keyring, was this one. I usually ask the students, is this a system? Now you can see that there are 4 keys, so there are 4 components on a keyring, and there's a handle. Forget about the handle, just a keyring and 4 keys. So is this a system or not? This is a very easy question I used to ask. I'm not asking this question because everybody knows the answer by now. Is it a system? Can it be a system? Under what conditions? Okay, the answer is associated directly with the concept of emergence.
They are not related.
Can it be a system?
They are needed both, just one for.
Yes, that's the answer. Okay? If I need all the keys together to enter this building, for example, one key opens to my room, for example, then you can consider it as a system, because when they all act together, an emergence, a result emerges. What is that result? The result is that I am able to enter my office. If I have one key missing, I won't be able to enter the office. Okay? But if all these keys are unrelated, one is for my office, one is for my house, or one is for the mailbox, etc., then they won't constitute a system. The defining property of a system is that the components, when act together, should do something that you cannot do by losing one of these, at least one of these. Of course, in Aker's readings, articles, you can go into the particulars of this. For example, some components may not be necessary for emergence, but some components are necessary. Aker's called those essential, essential components, etc. There are such details. These emergent properties can be desirable, or they can also be undesirable. That's another point we make. Transportation is an emergent property which we would like. But for example, the traffic, a car and road network, a traffic network, provides transportation, but also it provides noise and pollution. So noise and pollution is another emergent property of the transportation system, which is not desirable. So emergence is something like this, which can be desirable, undesirable, which brings us to the end of this lecture. Now, emergence and other properties of systems will be much better understood in our next lecture, which is on complexity. Let's go right over into this. Complexity, well, you know that we don't have a chapter in the textbook on complexity, but we have some readings, and actually we have one reading written by a physicist from MIT, Baranger. He wrote that article for people who are not physicists, but it's a very, very good article. I think it's the best article on the subject, which is serious enough but not too difficult to understand by somebody else other than physicists, I mean. And also to make that reading easier to understand and maybe to add some other notions, I have some notes also called Notes on Complexity that I hope that you have read by now. Now, let's, this PowerPoint summary is a summary of my Notes on Complexity. I have revised it again last week. I have made it longer and easier to understand compared to previous versions. So please make sure that you read these, all right? Now, parallel developments can be observed in history. One area of development or one avenue of developments are called systems studies, and the other one is the complexity studies. Systems literature and complexity literature have accumulated in the past more or less independently, separately from each other. But now they are coming together. Parallel developments that are joining together, and we shall argue why they are now coming together. Now, most systems of interest to us are complex, although we haven't defined complexity properly. To understand the causes that gave rise to these developments, I mean, one point why they are coming together is that systems literature and complexity literature are merging because most of the systems that we are interested in are complex systems. So these two are related. To understand the causes that give rise to these developments, we need to understand how science and the scientific method works. Let's just refresh our knowledge about our comments about science and the problem of knowledge. Now, ways to knowledge. How many different methods of knowing can we think of? Well, there's the authoritarian and mystical mode versus the rational mode. Fundamentally, there are two ways of knowing. One is the rational mode of knowing, and the other one is the authoritarian mode of knowing. The authoritarian mode used to prevail until about the time of the scientific discoveries of the 17th century. Starting in maybe the 16th century, it slowly developed in the 16th century, 17th century. and culminated at the end of the 18th century. Up to that time, true knowledge was assumed to be known to authorities, and you asked them. Religions, for example, played this role very, very effectively for many years. The rational mode is started with the age of enlightenment. Galileo and Newton are important. It doesn't mean that Galileo and Newton are the initiators of enlightenment. Actually, Newton is the culmination, is the end of enlightenment. Not the end of enlightenment, but at the time of Newton, this movement had matured well enough. The philosopher, the philosophy of enlightenment, I haven't mentioned his name, is best summarized and articulated and put forward by the philosopher Immanuel Kant. Immanuel Kant could also have been mentioned here. I have mentioned just a scientist. The Newtonian mechanics that Newton produced had a very, very huge impact on the way we understand the world, as we have argued before, and it has changed the way of knowing. And science emerged as a result of this. We can say that the aims of science is to search for reality and truth. We have explained what reality and what truth is. The objectives of science are explanation and prediction. Natural phenomena are observed, and we would like to explain why and how this phenomena takes place. And once you explain, of course, then you can make predictions about natural phenomena. These are the fundamental objectives of positive sciences, let us say, or the hard sciences, let's say. Understanding could be another objective, but some of the positive scientists, for example, physicists and chemists, probably, some of them will object to this and say that we don't need, science doesn't have an objective of understanding. Just explanation is sufficient for understanding. But understanding as an independent objective can be proposed in the case of human sciences. Understanding here is usually also termed in the German word Verstehen. It's called the Verstehen tradition. If you accept the Verstehen tradition in science, it means that you also have to seek reality and truth by putting yourself in the shoes of the object. You need empathy. You need to see the world from the eyes of the person that you are studying. That can only provide understanding. Understanding is important for us. Now, Eckhoff uses understanding and explanation in slightly different ways. So these are everyday words that we use in everyday language. They are not scientific terms, explanation and understanding. So sometimes usage can change from one source to the other. But I think it's clear what we mean by understanding this. And as a result of these processes of the development of the Newtonian mechanics, also the method that was used by Newton also developed into what we call the scientific method. It is closely associated with what we call positivism in sciences. The defining attribute of positivism is the assumption of objectivity. I have discussed this in detail in the past also. You remember there is a research cycle. There is the theory. Actually, we discussed this only yesterday. There's accumulated knowledge that you can call theory. Then you come up with hypotheses, and then you use observation and experimentation to see whether the hypothesis is refuted or rejected or not. And if a sufficient number of tests are passed by not being rejected by the hypothesis usually can be generalized. becomes a generalization, and that is an accumulation that makes an accumulation or addition to theory. This is the research cycle, and this is what we mean by the scientific method. But let's take a break.